There we go. Yay. Okay. So happy Thursday. Yay. Thursday of week 3. We're doing great. So remember, we do have a test on next Tuesday. Just thought I'd throw that out there. It's our first test. First tests are always scary because you don't know exactly what to expect. Um, what's I gonna say? There is that I'm hoping you checked your email. There's that practice test, and you will need the Respondus lockdown browser. The practice test has nothing to do with content at all. It is only for testing the software. That way, you know it works before you're actually taking the real test. So there's no content at all. There's no notes needed or anything like that. There's just a couple of quick questions just to it is timed, but it's like 60 minutes and there's 4 questions. And one of the questions is 2 + 2. So that it will take you all of 2 minutes to do the entire thing. But it's just timed just because I want to make sure that everything is working correct. So it gives you 60 minutes to answer 4 questions that are like, what's 2 + 2? And write yes in this box, things like that. So it's really super, super easy. It'll take you literally 2 minutes. So the timer is just because I want to make sure you get the full experiment. You like that, Jennifer? Yeah. I always have to throw a funny question on there. I used to have another question on there, but I had somebody get mad at me about it. I asked the question, the old question I asked about was something about if calories count if you eat them in a movie theater. And someone told me that that wasn't a good question, so I threw that one out. But that is a good question. I think it's a good question. I don't think calories eaten in the movie theater count because it's dark. Yeah, exactly. See, they don't. It's dark in the movie theater. Calories don't count in the movie theater. So I'm glad y'all agree with me. I knew you all were my people. I knew you were my people. Okay. So today, how are you supposed to count in the dark? Okay. We're going to draw and interpret scatter diagrams today. So that's going to look just a little bit different. We're going to be dealing with 2 variables that are affecting the same thing. We're going to talk about correlation coefficients, which is a lot of words for something that's fairly easy to find using the fancy schmancy calculator. We're going to talk about whether or not a linear relation exists, and then talk about really like 1 page really quick, talk about correlation and causation, and going to find the least squares regression line. So we're going to go back to algebra 1 and look at linear functions. I'm going to walk you through lab 3. Lab 3, once you collect your data, is fairly simple and quick, but you need to collect your data, and I will walk you through that. So that's today, and I'm excited. I enjoy this particular lesson, and I'll tell you again at the end, but I'm going to tell you right now, on Tuesday, this coming Tuesday, because it is the day the test opens, every time the day the test opens, we don't have new content in class. I am here for an hour for an office hour. We can do drop in, and you come in and you can ask questions regarding something on the homework or something on the review, but you don't need to come to class if you don't need help. If you're feeling good, you don't need to come, or you can come and ask questions, and it's just office hours. There's no new material this coming Tuesday. It is office hours only. So you can pop in anytime between 5:30 and 6:30. And it'll be in this Sunday's email as well. And it's on the syllabus. So this coming Tuesday, it's the day the test opens, no new material. All right. So let's flip over to our first slide. And for some reason, I didn't set it up for silly me. I didn't set it up to be single page mode. There we go. All right. So our first slide. So here's some vocabulary. So a response variable, we have a response variable and an explanatory variable. We hardly ever say predictor variable. The response variable is the dependent variable. It's not the one that drives the bus. It's the thing that happens because something else happened. It's going to be explained in terms of the independent variable. So it's usually like if you were using your y equals mx plus b, the response variable would be y. I can explain y in terms of x. So this would be the Y, this would be your response. Your explanatory variable is also like the independent variable. This is the one that makes things happen. That would be your X. This would be your explanatory. It is usually what you input to get the response variable out. So for example, miles per hour. Hours are the independent variable. They are the explanatory variable because you're not going any miles if time doesn't pass. How many miles you go depends on how many hours have passed. So miles would be your response variable or dependent variable that depends on how many hours you've been traveling. So response variable would be miles and explanatory variable would be hours. Okay. A scatter diagram, it's just a graph. It shows the relationship between two variables. It's just dots on a coordinate grid. It is a nice scatter diagram. We just plot the ordered pairs and you have this nice pretty pattern, whatever comes out. That's a scatter diagram. We're going to be doing that with Excel, and you're not going to have to do these by hand. We're going to do one by hand just in our notes, but even in hand and homework, you're not going to have to do one by hand. All right. So here's our first data set. Okay. So what this is measuring is where we started digging with a dry drill. We're trying to say, how long does it take to drill 5 feet when we start at different depths? So if I start at 35 feet, it took me 5.88 minutes to drill 5 feet. Starting at 190 feet down, it took me 7.9 minutes to drill down 5 feet. That's what this data is telling us. So the response variable would be time it takes to drill. The explanatory variable would be the depth at which we start drilling. And this is because if I don't start drilling, I'm not going to drill 5 feet. We can't start timing it until I start drilling. Okay. This is the scatter plot for that particular data set. Nice, pretty scatter plot. You notice as the depth goes deeper, the trend is that the time takes a little bit longer. Not always, but pretty much most of the time. As we get up, you can see that we have this nice pattern that is moving upward. And I don't see this nice pattern that's moving upward there. It's following an upward trend. If we were talking about slope, going back to our Algebra 1 days, it has a positive slope because it is going uphill. As my X value is getting bigger, my Y value is also getting bigger. Excuse me one moment while I grab my water because I'm feeling my throat's dry. All right. All right, let's continue. This is what makes you feel for the podiatrist? What? Fear the podiatrist? Why are we fearing the podiatrist? Drilling feet. Oh, gotcha. Oh, I'm sorry. Why would they be drilling? But so 2 people, is it that 2 people have both their feet drilled and the other person has 1 foot drilled? Or are there 5 different people that each have 1 foot drilled? Which is the case here? Because if the podiatrist is drilling feet, so 5 individuals' feet. Okay. All right. That took a dark turn. So a golf pro is investigating the relationship between the club head speed of a golf, measured in miles per hour, and the distance in yards a ball travels. So he knows there's other variables there, so he's trying to minimize those. Sometimes other things affect it. So things like club type, ball type, golfer, weather conditions. So they took the same golfer, did all of it. They had a nice 70-degree day with no wind, kind of like what's outside right now, but there's a slight breeze. The same golfer, the same kind of ball, the same club, all of that stuff. Then they're recording the club head speed. We're going to draw a scatter diagram of this data. If you printed this out, feel free to do this with me. Otherwise, you can just watch and be in awe of my mad graphing skills. And I'm going to use pink because why not? All right. So at 100 miles per hour, club speed, the club speed is on the horizontal and the distance is on the vertical, because if I don't swing the club head, it's not going to go anywhere. So the club is the explanatory variable and the distance is the response. So I'm just going to plot these points, 100 to 257, and we're just going to have to guess where they are because you're not going to get exact. So we're just going to have to guess where these things are. 103 to 274, 101, 266, 105, 277, 100, 263, 99, 258, 105, 275. All right. So I have all of my lovely data graphed here. It looks pretty clearly. I mean, if the club head is going faster, the ball is probably going to go further. So that makes sense. It makes sense that it would be that trend. And who knows what factors actually happened while he's swinging the club head. Like, look at the 102 where it's a little bit lower than the 101. Quite possibly he had a little twist in the way he was standing, or maybe he hit a weed weird. I don't know. I don't know much about golf, but obviously there is this upward trend here. I'm going to pick a prettier color so you can see that it is going positive here. So we have a positive slope. This is what we would expect. Questions so far? We doing okay? Okay. All right. So this is the different ways that we can see a scatter diagram. We're going to talk about the linear relations. So take a look at the first one. This is definitely linear, and it is also positive linear. And it just says linear, but this is a positive because it has a positive slope. And this one right over here, the next one, this one is a negative linear because it has a negative slope. It's going downhill from left to right. We read graphs from left to right. It's going downhill. It's a negative linear. So the bottom left, you can't say that it has no relation because it is clearly quadratic. It clearly has some relation, but it's not a linear relation. So you can't say there's no relation. You could just say no linear relation. So I would just say this. If I was answering the question on a test or a quiz or homework, I would just say there's no linear relation. Same thing with this one right here, also no linear relation. There's clearly a relation. That one's actually cubic. The one on the left is quadratic and the one in the middle is cubic, but it's not linear, clearly not linear, but there is a relation, just not linear. This one over here is completely scattered, the one on the right, and this one doesn't have any relation. I probably still would just say no linear relation, but there's not really a pattern here. It's just there. So I would still just probably say no linear relation, though it just says no relation here. Questions? All right. I already said this on the other one. Positive association is when as the dependent variable increases, the independent variable also increases. Negatively associated if when one variable gets bigger, the other one gets smaller. So if they're both getting bigger, it's positive. If one's getting smaller while the other getting bigger, it's negative. So if it's going uphill from left to right, it's positive. If it's going downhill from left to right, it's negative. Okay. Once y'all make sure you tell me to slow down if I move too fast, because sometimes I do. Sometimes I get excited. So I love the math. I know I'm a weirdo, but I do love the math. Okay.
I have a question.
Yes.
I joined in kind of late because I just got off work late, so
Okay.
hopefully this hasn't been asked.
Uh-huh.
I'm still a little bit confused about the dependent and the independent variable.
So the independent variable drives the bus. The dependent
Okay.
variable doesn't happen unless the independent variable happens.
Okay.
And for example, miles per hour. If no hours pass, I'm not driving anywhere. If hours pass, then I can tell how far I've driven based on how many miles or hours have passed. What, like this one that we just did back here, club head speed. So spinning a golf club and our club head distance, and it's making the ball go. If I don't swing that golf club, the ball's not going anywhere. So the independent variable is I can swing this club head without the ball going anywhere, but the ball's not going to go anywhere unless the club head swings. If that makes sense.
Yeah, I think I'm starting to catch on.
Okay.
Sometimes just like when there's like using time in other places, but sometimes that one's a dependent. So it's just,
Yeah, it really depends. But and most usually it's like one thing makes the other thing happen, or one thing can be explained using the other thing. One of the variables is usually driving the bus. There are times when neither one seems to be driving the bus, so you just choose. Like my example, when I do the lab, neither one of them's driving the bus. You just got to choose.
okay, thank you.
Yes. All right. This formula I will never, ever, ever, ever make you do. I just put it there to scare you. You will never, ever, ever have to calculate this. So if you were scared, that was the point, but you never have to calculate it. All right. Correlation coefficient. Now this helps us to determine how strongly two variables are correlated and the direction of the relationship. So I could say that they have a strong correlation and they're positive. Strong positive correlation means it has a positive slope and it is really close to a line. So if we were doing the population correlation coefficient, we would use this right here, which is rho. It's a Greek letter rho, but we don't really need that if we have the entire population. So we pretty much never use it. And it was almost pointless to even tell you. Instead, we use a lowercase r. And this is our correlation coefficient. So sometimes we just call it an R value, and I'm going to write that down. Sometimes we just call it an R value. This is value. I have a really bad habit of making my V's look like U's. We'll call it an R value, or it is the correlation coefficient, but I will use them interchangeably. It's just because correlation coefficient is a mouthful. It's a lot to say. So I'm going to show you how to calculate it, but we're only going to do it using Excel and using your calculator. We're not going to do it by hand, though it's actually kind of fun. Right. So these are some things about it. I'm not going to ask you these things. I'm not going to ask you to repeat them, but there's some things about the correlation coefficient you should know. And it's always between -1 and 1. It can be -1 and it could be 1, but it's not going to be any higher. So it'll be goes from -1 to 1. A +1 means I have a perfect positive linear relation. If it's -1, I have a perfect negative linear relation. As it gets closer and closer to 1, it is closer and closer to a perfect linear relation. It's stronger and stronger positive association. So we get closer to -1, a stronger and stronger negative association. So it's getting really close to a negative sloped perfect line. If we get close to 0, then there's little or no evidence that we have a linear relation. So super close to 0 doesn't mean that there's not a relation. It just means it's not linear. We only use the correlation coefficient for linear. It doesn't have any kind of units. So we don't say like R miles per hour. There's no units. It's just R. It just is what it is. And what it means by the correlation coefficient is not resistant. So this right here, what that means is that if there's an outlier, it's going to drag my correlation coefficient in the direction of the outlier. It just happens, or it's going to make it worse, make my correlation coefficient less linear. So it does affect it, kind of like it affects the mean and standard deviation. Questions before we move on to math? All righty then. Let's take a look. Letter A is perfect positive. See, it's a nice, perfect straight line. Letter B looks pretty darn close to perfect. There's a little bit of things outside of perfection, but it looks pretty close to perfect. B is not perfect. It's about a 0.9, so it's pretty close. Now, letter C, it says it's 0.4, but I think that that's not true. I would probably say this to me looks more like a 0.6, which is still pretty moderate. It doesn't look like a 0.4 to me. We play a game in my high school stats class where they guess the correlation coefficient. So I've seen a lot through guessing, and it really looks more like 0.6. Letter D is a perfect negative. It's perfectly negative, perfect, beautiful line going downward. And E is pretty much similar to B. It's about a 0.9. Once again, now this one right here, this outlier right here could drag it to 0.4. So that's possible it's negative 0.4. Though overall, I mean, I think it's a little bit better than that. It's probably a 0.5, negative 0.5, but it's still going negative and they're still moderate. Letter G, pretty much nothing. It's just completely crazy. It is pretty close to 0. There's no line in there. There's no trend in there. And B is a nice, pretty parabola, or H, I mean. It's a nice, pretty parabola, but it's not linear. So our correlation coefficient would be close to 0, but it does have a relation, just not a linear relation. Any questions on any of these? All right. I want to do the math. Yes, we're going to do the math. You will need your fancy schmancy calculators. You will need those. I'm going to go over to my fancy schmancy calculator. What we're going to do is we're going to put these into our calculator and we're going to run something called a linear regression. And it's going to help us to find that correlation coefficient. Okay. All right. So, just a second. I just lost my train of thought. All right. So in our lists, so hit stat and edit. In our lists, I'm going to clear L1. Remember, hit clear enter. Don't hit delete. Clear enter. I'm going to clear my L1. I'm going to put all of the depth at which drilling began into my L1, and the time to drill will be in L2. So I'm just going to put these in here. You go ahead and do those along with me. Okay, I'll give you a second to get caught up. H would not have an R value, no. I mean, the R value would be 0, Quentin. You need to know the word correlation coefficient. Well, you're gonna need to, you don't necessarily need to say it to me. You can say R value, but you'll be asked for it. So as long as you can recognize arch word with arch, oh, parabola, no. You don't need to know the word parabola. Okay, and now I'm gonna put in the numbers from the well drilling, how long it takes. So parabola is a fun word. It's a great word to pull out at parties. And if they don't appreciate it at parties, you're not going to the right kind of parties. I just realized I missed one of my numbers because I think I did. Maybe I didn't. I just doubled up. Don't do that. Okay, 7.97, 7.62, 6.89. Uh-oh, I did mess up somewhere. I hate when I do that. Okay. This is the most common error is typos in your calculator. 6.42, 7.97, haha, 7.92. This is my issue. 7.62. There we go. 6.89 and then 7.9. That's my most common error is the typos in the calculator. All right. Give you all another second to get those in there if you haven't already. Does anyone need another moment to get those into your calculator? I'm happy to wait. All right. So now hit the stat button and go over to highlight calc, the same screen we were using before. But now I want the number 4 option, linreg AX plus B. It says linear regression. AX plus B is the form we wanted in, like y equals mx plus b, but instead of m, we're using a. So I'm going to go down here to number 4 and hit enter. My list 1 is my x values. Those are my independent variables, L1. And then L2 is my Y list. If you don't know how to do L2, it's second number 2, and that gives you L2. Leave frequency list alone. Leave store reg EQ, leave that alone, and just go down to calculate. So it should look like this. Then we hit enter. Now, many of you may not have an R squared or an R value. I'm going to show you how to get those because some calculators have been reset or something. So if you don't have the R squared or the R value, let me show you how to get those. All right. You typoed. Yeah. Why did you delete the whole thing? Okay. So I'm going to do second and then 0. Notice how it says catalog right above 0. So second 0 gives you a catalog. Scroll all the way down to diagnostic on. So see here as diagnostic on, and then hit enter, and then enter. Once you do that, you will then have the R squared and the R value. So then hit stat. TI-83, does it give you the R value and the R squared? No. Does it have a catalog? You may need to Google it if you don't have a catalog. I think it has a catalog. I think if you do second 0, you should get a catalog. Let me look on mine. Yeah, I have it on mine. If I do second 0 on my TI-83, I can scroll down to diagnostic on and it's there. And then just hit enter, enter, and it's there. Because I have a TI-83 right here in front of me. It does the same thing. Okay, go back to linreg, and now your R and your R squared should be there. I'm going to explain the R squared really briefly because, let's see, R value. Because I believe that it asks you for it. We don't use it a lot, and I think there's one question that talks about it. So what the R squared value is, other than just your R value squared, what the R squared value is, and this is kind of hard to explain, it tells you the percent of the variability of your Y value that can be explained by your equation. So I'm going to just write the equation, even though we're doing the equation later. So notice how it says Y equals AX plus B. That is the same thing as Y equals MX plus B, except for my A is my slope. So it's 0.016 X plus 5.527. So my R squared value is about 60%. So what it is saying is that 60% of the variation in the well drilling, the time it takes to drill can be explained by my equation. So basically using my equation to make any predictions, there's only about a 60% chance it's going to be correct, which is not super great. So thinking about the strength of your prediction, you need to look at that R-squared value. So I'm going to go back to the other screen. But that's not how I do that. Wrong way. Okay. So back at my other screen, I put the equation here. So this equation right now, if I use this equation to make a prediction about how long it's going to take to drill at a certain depth, it's about a 60% chance of being right, which really is not that great. But at least I can get a ballpark, right? So this R value right here that we just got, this lovely R value, this R value tells me how strong my linear relationship is, how strong the linear relation is. I generally, I would say 0.77 is moderately strong. That's probably what I would say. One thing that is tough about linear regression and stats in general is there's not like these rules that these are the rules. This is written in stone. This is the rules we use. There's a lot of things that have wiggle room, because if I'm building a space shuttle, even 0.9 would not be a strong enough linear relationship to whatever I'm building. But if I'm planting a garden in my backyard, I might think 0.77 is a pretty decent linear relationship. You see what I mean? So it really depends on what you're doing, on how strong you feel that linear relationship is. I'm going to give you a, I don't even know what to call it, but kind of like Kleist rules. The way that I do things is this, I'm trying to find a good spot. So I'm going to go on the next screen. We're not going to touch it yet, but basically the way that I do it, this is like my brain. Anything about 0.85 and up, I would say is strong relationship. Usually 0.85 or up, I will say it's strong. I would say relatively strong. I'd say about 0.65 to about, no, probably not even that. Maybe 0.7 to about 0.85. I would call it about moderately strong. Personally, that's about where I would go. Probably about 0.55 to about 0.7. I would say that it's just moderate. 0.45 to about 0.54. I would say that that would be moderately weak. Weak. That's not the right weak. Weak. And anything lower than 0.4, I would say is pretty weak. So probably about 0.2 to about 0.44, I would say weak. And then anything else, I'd say either, so under 0.19 down, I would say either very weak or virtually no linear relation. Now, I'm not gonna, this is not the rules you have to follow. This is just approximately where Kleist does it. So approximately like Melissa's rules of law, not really. Melissa's guidelines, maybe. So, I mean, if you had a 0.78 and you decided to call it strong, I'm probably not going to mark you down. But if you had a 0.25 and you called it strong, I'm going to mark you down, if that makes sense. So just ballparks. So just depending on what you think, just kind of ballparks. I mean, even if you had a 0.87 and you called it moderately strong, I'm on board with that. But don't call a 0.2 moderately strong. Don't call a 0.05 moderate. So you see what I'm saying? Picking up what I'm throwing down? Questions? Okay. I would like you to put the club head speed and distance data into your calculator and go ahead and run the linear regression. So go ahead and run this linear regression, use this data. And I'm not gonna delete this until I'm not gonna delete this stuff until after you've done that. I'm gonna put it on my hand calculator here. We'll see how we do. You're looking for the linear regression or the correlation coefficient. Don't ask me, I don't know what I'm talking about. You're looking for the correlation coefficient. And if you forget what to put somewhere, feel free to ask me, I'll tell you. It's to turn on the R squared, you put second catalog, so second 0, and then go all the way down to diagnostic on to turn that on. So go to all the way down to diagnostic on, hit enter, enter, and it should then go back in and run your regression. It should be in there. Okay, I'm going to erase this stuff now. Okay, that definitely is not a correlation coefficient. That's your B. The B is your y-intercept. You got the y-intercept right there, Clemencia. You should look at the R value. So, okay. Quentin, you have the R squared. Yes, 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 yes. So my R value, oh, that's the wrong thing. So the R value that it looks like everybody in the comments is getting 0.939 approximately if I round it. So would you all consider this a strong linear relation? So what is your error message? What error message did you get?
Oh, I put in my information and then I do the stat and then I hit 4 and then I do the second 0 and hit the catalog.
No, 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 no. So you only need to do the catalog once. After you do it once, it's going to be there forever unless you reset your calculator.
Gotcha. Thank you.
Okay. Okay. So Clemencia, you need to go into do the second 0 to get to the catalog and go all the way down to diagnostic on and then hit enter, enter on diagnostic on, then go back and run your regression again. You'll only have to do that once until the calculator's reset. If the calculator gets reset, then you'll have to do it again, but otherwise it's just a one-time thing. These calculators can do so many cool things. It is crazy. There are dice simulators on here. You can have like custom wheels to spin. There's all sorts of super crazy things. Okay, so I would call this a very strong correlation. For my R squared value, for R squared, we got 0.88. So what this is saying, yes, good. So what this is saying is that 88% of the variability of the club head speed can be explained by the equation that we get from this. So I could be pretty confident that I'm going to have a fairly accurate prediction if I use my equation, which is kind of cool. So I could use the equation to guess how far it'll go if, let's say, my club head speed was 104 miles per hour. Now, no matter what, you're not going to want to make a prediction too far away from your data, because the further away you get from your data, the less accurate it is. So I probably would do the 88% of the club head speed can be predicted by the equation that we get by running this regression. I mean, not the club head speed, the distance. Sorry, Jennifer. So 88% of the distance that the ball travels. So it can be predicted by our equation, the variability there. So I'd have an 88% accuracy rate predicting, if I was predicting near the data that we have. I would not want to predict what happens if I had 120-mile-an-hour club head speed. It's a little too far from my data. I would not want to predict what happens if I had a 50-mile-an-hour club head speed. That's a little far from the data, but I could go a couple miles per hour one way or the other. I could do like 95 degree or 95 miles per hour, or maybe up to 108, 109 miles per hour. Just don't go too far away from it. And I don't really think you're going to be, you're definitely not tested on R squared. R squared is used more in later math classes, but I want you to be, so the club head speed is the explanatory, yes, and the distance is the response. So the response, 88% of the variability in the response can be explained by the equation we get. Yep, good. All right. Let's talk about equations. I think that's what's next. Oh, nope, correlation doesn't equal causation. Okay, this is fun. I'm going to try to jump into, there's a website, if I can get to it, I want y'all to see it. It's hilarious. So if you have observational study, so anything where you are not causing things to happen, you are watching things happen or just collecting data from things that happen, you cannot say that correlation equals causation. Even if I have 100% correlation between two variables, I can't say that one thing caused the other. You can't say it. So here's an interesting example. So the correlation between teenage birth rate and homicide rate since 1993 is 0.9987. However, you can't conclude that higher teenage birth rates caused the homicide rate because it was observational data. So if it's observational, you can't say that something caused the other. I'm going to jump really quick to this cool website. Let me see if I can get there. Get rid of this so I don't accidentally go there again. Okay, so it's called Tyler Vigen, and it's called spurious correlations. Just a second, let me get to the spurious correlations. Here he is. This Tyler Vigen guy, I mean, I don't know much about him, but I know that he makes really fun graphs. So let's see if we can get there. So take a look at this. So this correlation right here is the number of websites on the internet correlates with total wind power generated globally. There's a 0.978 is the correlation coefficient. There's some really funny ones in here. Let's see if I can find ones. Population of the name Tiffany is correlated with the air pollution in Los Angeles. There's a 0.966 correlation coefficient. Now, we can't necessarily say that naming your child Tiffany causes pollution in Los Angeles, but I guess we can't say it doesn't, right? There's a whole bunch of really fun ones. This is cool. I like this one. Google searches for "my cat scratched me" correlates with the Coca-Cola company's stock prices. It's a 0.974. It's a pretty strong correlation. It's just, there's hundreds of them on this site, hundreds, and you can create your own. I will write down what it is. So if you decide you want to go there, you may, because it is a really fun, I mean, you could probably see it yourself, but you know, I'm still going to write it down. Tyler, it's okay, go back. So wrong way. So it's tylervigen.com. It's like his personal page, but there's a link on there to get to the spurious correlations. Or if you just Google Tyler Vigen, one of the top responses is that site. There's hundreds of them and they're hilarious. I show one a day to my stats kids at the high school just because they're fun. And because I'm weird and like things like that, but it's okay. You can be weird too. Okay. We're not going to deal a lot with lurking variables, but it's something important, and it's going to be something that you're going to need to think about when you get to your own final projects, which a couple weeks I will give you that. Lurking variables are things that aren't included as an explanatory variable, but they affect the relationship between the two things. So it could falsely identify strong relations. So it can make two things look like they're related when they're really not. They just happen to both be affected by this other thing. So here's an example of that. Air conditioning bills. A hot house makes you consider crime. So air conditioning bills increase when crime rates also increase. It doesn't mean you should turn off your air conditioners in order to combat crime. It just means the higher air temperatures cause both air conditioning bills and crime rates to go up. So it affects both of those things. So it makes both of those things increase. So there's that lurking variable there. And I'm not going to ask you about these, but it's something to think about when you're doing your own research later on. Save that for Facebook. Yeah. Okay. Now let's talk about the least squared regression line. We're really almost done. We're at 17 of 19. So we're really almost done. So a least squared regression line is also called a line of best fit. I jump back and forth between the two things. So what it does is it minimizes the vertical distance between each of the points as much as possible. So it basically goes through the center of your data. And sometimes, I mean, you can draw one yourself and get one pretty decent, but we're going to use technology, specifically our calculators, to find that line of best fit. And then we will use Excel. Most people on their final projects use Excel and create a linear regression, because one thing, it's pretty and it's nice to be able to correlate those variables and all of that. So it gives a nice linear estimate. And when our R squared value is really high, then it's going to be a good thing to use for predictions. So it's kind of cool. So we already got this line. So I already wrote that line down. I'm going to go back to the calculator where I had it before. You don't need to go back to yours. I'm going to go back to mine, because I still have my well drilling data here. So I'm going to make this bigger. When you run your linear regression, the A value is the slope. So notice it gives you y equals ax plus b right here. The A value is your slope. The B value is the y-intercept. This would be my least squared regression line. Usually I round to 3 or 4 places, depending on what I'm feeling at the time. Ooh. Okay, just a second. I'm going to write it down on my iPad and then I'll go over. So I usually, round to 3 or 4. So let me go back to my other screen. So that's my least squared regression line. So that's the line that best fits my data. But remember that we only have about a 60%, it's like 60% reliable, but I can it would help me to get a decent estimate. So let's say that I wanted to see how long would it take me to drill if I was starting at, let's say, 195 feet. It's still close to my data, but I want to know if I started drilling at 195 feet, about how long should I expect it to take me to drill? So I can take and put that 195 feet in for X. And I could get a prediction. Let me put that in my calculator and let's see what my calculator is saying to me. Whoa, that's weird. I don't know what I did. Oh, I forgot a decimal. I was like, that number is way too big. Okay, So I got 7.789. So I would expect it to take about 7.789 minutes to drill 5 feet if I started at 195. Now, remember, we only have a 60% accuracy here, but at least it kind of gives me an idea. I would be like, okay, I could expect this to take around 8 minutes, and that'd probably be pretty accurate. Questions on the linear regression, on the least squared regression line? Okay. Since it's already in your calculator, I would like you to write the least squared regression line for the club head speed data. It's already in your calculator. You might have to go back over to it and just run it again, even though all the data is still there. So go ahead and find that least squared regression line. Remember, the A is the slope and the B is the y-intercept. And the y-intercept does not necessarily make sense. A lot of times it doesn't. In fact, at this time, it really doesn't make any sense. I'm going to write it down. See how you did. How'd we do? Good, 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 good. It's good to hear some of you are getting it. Okay. So my y-intercept is negative 55.797. So if I was interpreting this, I'd be saying that if I have a 0 club head speed, the ball is going to go backwards 55.797 yards. See, it makes 0 sense, but a lot of times it doesn't make sense. It's okay. Because if you're not, there's usually like, they call it, they restrict the domain. They say this is valid for club head speeds greater than 60 or something like that. So they usually give like a range where this works for. We know it works at 100. We know it works all the way up to 105. But see, now I can use this. So go ahead and use this equation. Let's make a prediction. Let's do 108 miles per hour. Let's just do a prediction. Use your equation and calculate 108 miles per hour for the club head speed. You're going to put that in for X. Yep, that's what I got also. Wait, did I? 3.116, 108. I got 280. I'm confused. What did I do wrong? I probably did something wrong. Oh, did you guys do 3 point? You did 3.116 times 108 minus 55.797? Because I got 280.731. Let me try it again. Maybe let me see. Times one. Do you do 108 miles an hour? Oh, that's what you got? Okay. Oh, okay. I was like, who has 3.1? Oh, is it supposed to be 3.166? Oh, okay. That makes sense. Thank you. This is why I keep you all around. And you thought it was just for all your dashing good looks. Thank you for fixing my typo. I told you typos are the worst things, and it was actually a righto. So yeah, 286.131. Yay, we're all on the same page. Keeps me human, yes. It's another example of your math teacher is human. Okay. So 200, and make sure you put your units. So we would expect at 108 mile per hour club head speed, we would expect about 286 miles per hour would be the distance, or not miles per hour, miles. What the heck? The heck, Melissa? Okay. We would expect the ball to go about 286 miles. Miles? Sheesh, y'all let me write these things? Yards. That would be a really far ball going miles. Yards. Now I'm going, yes. So, and remember it said about 88% accuracy. That's not too bad. So I think that we probably could accurately predict it. I want Tiger Woods stuff there. Yes. All right. Questions regarding the regression line. Hopefully this is not too shabby. Lots of calculator work. So you would make the X on progressive relativity. Your brain's fried all week. Yeah. I don't know. Okay. I thought there was another one. Look at this last slide. Look how pretty that is. No, well, I just made an X up. I just made up an X. The X I just made it up. Yeah. And I just found an X value that's not too far away from my data, because I would not say 150 miles per hour, because that's kind of far away from my data, and we get less accurate the further away from your actual data that you go. So it's going to get less and less accurate trying to predict things far away. So you want to, if you're making predictions, you can make predictions for things close to it. If you're making predictions of things far away, you would have to put some sort of a disclaimer on it. All right. So that is it for the new material. We're going to do the lab next, unless does anybody have any questions on this material before we go to the lab? Funny, I said go to the lab like we're going to get up and go somewhere. We are not. I'm going to unplug my iPad, even though my battery's good. Unplugging it. This is my lab. This is lab 3. We're going to be running a linear regression for lab 3. You need 2 variables that you think may be correlated. So here I have imaginary friends, and I have, and it's, these are spouses that are male and female, and I imagined that they have ages, and I made the ages up. All of this data is made up. Mine can be made up. Yours needs to be sourced from somewhere, but obviously for this, I won't check your sources. We need to be a little bit more honest for sure. If you, in your final project, please do, if you make up your data, please don't tell me you made up your data. I didn't say that on camera, did I? That you can make it up. Don't make up your data. Honest, true, you know. Anyway, so your population, what is your population? My population is Facebook, I guess. I found people's ages. I don't care why you're interested. You don't have to tell me you're interested, but tell me what variables you're studying. I'm studying, this is like different amount of hen's teeth you found on the farm. There you go. So I'm taking married couples and taking the husbands and wives' ages. What are the units of my data? Years. Why do I think they have association? You need to talk about why you think that, even though it says, why are you sure? I want you to talk about why you think those 2 things are correlated. If you were doing coffee and number of hours slept at night, you would say, I think people who drink a lot of coffee probably don't sleep a whole lot. Tell me where you got your data. Do not use Google as a source. Google is not a source. Google's not a source. Pinterest is not a source. Nothing like that. If you go to Google and get a source, you click on a website, and that website is your source. Sorry. It's a pet peeve of mine. People do that sometimes. All right. So let's do a scatter plot. You need to highlight both of them. I don't know if I can highlight. I'm going to highlight the variable also. I don't know if this is going to work. I don't remember if this works okay. Let's try it. Highlight all of that. And once again, I'm going to go to insert. And if you do the recommended charts, it's going to give you scatter plot. This is the one I want. See, it's not going to do it the right way. It just gave me wife's age. Let's start over. I'm not going to highlight the top. Notice that the husband's age is first. Therefore, he is my X value. He is the horizontal axis. The wife's age is second. Therefore, she is the vertical axis. So insert recommended charts, and I've got a lovely scatter plot. I'm going to make it bigger, don't worry. And I'm going to make it here. And before you add any titles or anything like that, I was going to make it bigger. Before you add titles or anything like that, play with it and pick all the colors and anything crazy that you want to do to it. Do all of that before you add titles and stuff, because it might delete all that stuff. Change the colors. Maybe I like purples. Do I like purples? I like purples. Oh, I don't like that one. Okay, whatever. There we go. So play with it, and then you add your axis titles. Add chart element. I need a husbands. Okay. Facebook. Spousal ages. I don't know. Spousal ages. I don't know. So I'm going to add axis titles. I need a horizontal title. I need a vertical title. We always need the titles. You will get marked down without a title. So I'm going to put husband's age is my X value. Husband is age. And then here, I'm going to put wife's age. Okay, so in my case, I don't have an explanatory and a response variable. One of the things does not predict the other. I say that again, one thing does not predict the other, so therefore it doesn't matter which is which. If you think whichever one you think is predicting the other one, like for example, if I was doing cups of coffee versus sleep, and I'm thinking the amount of sleep that people get affects how much coffee they drink, I would put sleep as the X variable and coffee as the Y. But not everything has an explanatory and a response. It doesn't, and it's going to look the same no matter how you set up your axes. The next thing, I didn't mean to do this. The next thing you're going to add, so go back to add chart element. I want a trend line. So down here, second to the bottom, it's trend line. Number of car crashes on a rainy day. But what would your second variable be? Would you be number of car crashes and then the amount of rain that happened that day? I mean, that could work. That could work. Yeah. So the amount of rain would be your explanatory and the number of car crashes would be your response. That works. So we're only looking at linear. If I'm putting a trend line, I only want linear. Even if your data represents something else, we're only doing linear. So I'm going to click on linear. Look at that. So I'm going to click on this trend line. I'm going to click on this, double click on this, because what I want, I just double clicked on my trend line. Look down here at the bottom, display the equation on the chart and display the R squared value. I want both of those things on my chart. I'm going to move them over here and I'm going to make it bigger because I like it. I like these bigger. So you want the R squared value and the equation on your chart. You need to have those things on there. Put those on there. It will not give you the R value. It won't give you the R value. So what I did here is put R equals, I'm going to type it down here. This is not necessarily exactly how you need to do it, but you are going to need to reference what the R value is. And I'm just going to type in equals square root of this number right here, 0.8616, because we can get the R value by taking the square root of the R squared value. Now I have a number. Let me make that a little bit bigger so you can see it. Come on, make it bigger, bigger. Okay. And let's make this, move this over. Okay. My R value is about 0.928. That is pretty darn good. Down here, you're going to talk about how good the association is between your variables. I want you to reference your R value. In F, please reference your R value. And another thing and really important for me to say is this, when I take the square root of the R squared value, it will not give me a negative if it's a negative. So if you're going to have to look at your slope, if the slope of your graph is negative, you're going to have to mention down here that your R value is negative, that you have like a strong negative correlation. If it's negative, so if your graph has a negative slope, mention that when you're talking about it. Now's the time for questions. So using our example, what would I be sure that the two variables have an association? I would probably say that I feel like most married couples are really close to the same age. That's probably what I would say with my example. I would say that my guess is most married couples are close to the same age. Therefore, it would have a strong association or have a linear association. That's what I would say. Yeah. So just basically, if you give me a good story there or a good explanation, I'm not gonna mark you down for it. You just have to do your best guess. Why do you think that? Why did you choose these two variables and think that they had an association? Because that's what you're doing. You're choosing two things you think are associated. Like, do I think that taller basketball players make more baskets? Maybe. So I could take, the height of the basketball player and how many baskets they scored in a season. Do I think that, I don't know. Do I think that a heavier defensive lineman sacks more quarterbacks? I don't know. Find the weight of the defensive lineman and find how many quarterbacks he's sacked. I don't know. I'm making stuff up, but whatever you think, two things that might be correlated. All right. Other questions? Yeah, basically you think that X has something to do with Y. How many data points? Just 20. 20, I mean, it has to be two variables, 20 each, obviously. More is fine also, but at least 20. I will mark you down if you're under 20. So make sure you have at least 20. And you never know, you might collect these 20 data points and be like, I really like this. I'm going to collect 30 more for my final project later on. It might be something you like, because when we get to your final project, I know I keep mentioning it and I haven't given it to you yet, but your final project's going to have two variables, at least two variables. So you never know, you might find something you like and do it again. Okay, any more? Because we're still on record. So any more questions while we're still recording? Nope. Okay. If I can find my stop recording button. That's not it. I'm going to stop recording. Can I get there? How do I stop recording? I hid my little thingamajiggy and I don't know how to stop the recording. Can I do that here? No. Don't capture me on my screen. I don't know how to get the tools back once I got rid of them. Oh, there we go. I'm like, what did I do? Okay, stop recording. Yay.